Hi. This video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not meant to be a tutorial, it's just me learning game programming. Enjoy the video. Yes, it's time for part 10, I believe, and I added myself in the corner, just as an experiment. We are doing Sprite to Sprite collisions in this part, and it's going to take a little bit of explaining, mainly because we're trying to find out what, we're looking at the code, we're looking at the solution, and we're trying to find out what the problem was that the programmer was trying to solve. And in this case, I really had to do some thinking to get there, but it's not so much code, so it should be easy. Let's look at the constants here. Let's see if we have anything that's different. So far, no. There's the objects that we had last time. Oh, we have an object height. And the object height is 8 characters times 2, because the hitbox was 2 characters high. So 8 times 2. Could have been 16, it's just 8 times 2. Now, let's look at the main loop, because something has changed there. Here's what we do. Still a wait frame. Then there's the object control. This takes care of moving the player as well as the objects. As we saw last time, we basically used the move player code, but we've made it so that it works for the objects as well. So, except for the gravity. So objects don't fall yet, but shouldn't be very hard to do that. And note also that object control, there's no collision calls. There of course there's collisions with the characters. Certain characters cause block the sprites, but there's no sprite to sprite checking in the object control. Now, as long as sprites, enemies or players, move at 1 pixel per frame, there's not really a problem. But we also know that to make certain moves possible, like fall speed and the jumping, we have to make those sprites move several pixels within 1 frame, within 1 game loop, actually. And during those, there's no collision checking. So during a jump or during a fall, you cannot, as the code is now, your collision with another sprite, with an enemy, will not be detected. So after we've moved everything, then we check for collisions. So we check for sprite to sprite collisions. So that's where we go. Now, that code is right below here. Enemy versus player. It uses X as an index, but that's quite, that's not uncommon. And we check where we start with checking from object 1 on. Object 0 is a player, so we're checking whether an enemy is touching a player, yes or no. That frees up there's a possibility of doing something when 1 player hits another, but we only have 1 player at the moment. So, then there's a collision loop. Basically, what it does, it looks at the active sprite, and it checks if that sprite is active. So it basically goes through all the enemy sprites And only if it's active does it check the object, and otherwise it just increases the index. If it's at the end of the table, then that's the end. And if it isn't, we go to the next sprite in the loop. And when there's no sprites left to check, the border color goes to 0, so it goes black. We're aiming for a white flash when there is a collision. Maybe we should look at that. Why don't we try and run it and see what happens? There's one thing that I've just noticed. Maybe let's see if you're noticing is this sprite and this one. There's no blocking. Why are these characters not blocking the sprite? These must be a lower number. And this one, it's even more. Let's start over. I just noticed this. So this sprite goes up, goes up, goes up. It's not blocked, but it's being blocked now. So why is that? Anyway, when I touch a sprite, boop, I get a white border. See? There it goes. So that works. And I get a black border when there's no touching. That's basically the thing. Okay. I don't think I'm going to answer that other question unless I happen to run into it, but it has to do something with the going up code. I don't know. Different subject, that. Check object. There we go. What we do is we had X. We store that. X is the index into the sprite active table. We jump to a subroutine that checks, is the enemy colliding with the player? That sets a value of the accumulator. So if that is not 0, then we were colliding. Otherwise, we take the parameter back, which is the original index, because it's probably been destroyed by these by this subroutine, and then we jump to the next object. But of course, we're interested in the case, what is the enemy colliding with player. By the way, if the enemy is colliding with player, we get the number 1 color, which is white in the border, and then we jump out, which means that at any collision, we jump out of this loop. So we're not able to detect multiple simultaneous collisions at this moment. But there's and this code actually exists, is that the object is removed. We load X with 0 and we remove object 0. So that's the player. So this code exists. So that's funny. Anyway, this is the place where we've detected that an enemy has collided with a player, and this is where the fun stuff happens. What happens? So you don't die immediately, of course, but I think that's what he wanted the direction he wanted to take. So is enemy colliding with player? That's the meat and potatoes of this thing. Now, first off, you get to a zone. A zone is nothing but, a namespace where labels like these have meaning, and outside of the zone, they don't have meaning. So you can reuse labels if you wanted to. It's just a namespace. But the function, this is not the function, because the function starts here. Now, bear with me, because this is where it happens, okay? First of all, we take the... to detect a collision, you can split the work in two. If you have two sprites that are that have a vertical distance from each other, they can be close to each other in the horizontal plane, but if they are vertically away from each other, if they're not touching vertically, then they're never going to be touching. So you can check the Y part, and then if the Y part says, hey, this might be a collision, you have to check the X part, because the other way around it works the same, of course. If two sprites can be on the same horizontal plane, but vertically different. Did I say that right? I don't know. Anyway, we're doing the vertical checking first. So what we do, we go to the sprite position. These are not the character positions, but the bit positions, right? So we get the Y position for the sprite that we're checking. Now, I'm not going to go into that, but when you add, remember that before you add, you had to clear the carry, because you're adding with carry. Subtraction is the same thing. You cannot subtract without the carry, but you have to have the carry set before you subtract. So we set the carry and we subtract the object height. Now, I'm going to drag in our zoomed in screen again. So I'm gonna draw a character. This is, each block here is one character, is 8 by 8. So our sprite, our hitbox, is this size. Now, if a sprite was touching, and I'm drawing it below. Yeah. If a sprite was touching, and remember that the sprite position is about this bit right here and this bit right here. So if I took the sprite position from the table, and any number that is there is the position of that pixel of the sprite. Now, if I let's have a peek. Okay, we subtract the object height. In this case that I've just drawn here, this sprite, we say, is now touching the player. Yes? So, if we subtracted the object height, which is this distance from here to here, that would mean that the coordinates of both the player and the enemy are the same, right? If the sprite was here and I subtracted 16, I would end up here, and that would mean that they wouldn't be touching. So in order to check whether or not these sprites are touching, I put it in the edge case, in the case where it's just touching or not. This is just touching. If I subtract the entire height and the result is 0, the result is the same, then they must have been touching. Okay, so let's go back to the code. So we subtract the object height, we compare it to the enemy, to the enemy's Y position. Remember that this is the same table, but with no index, it returns the first value, which was the player value, so we're still doing that. So we compare the enemy's Y position, which is in the accumulator, to the player. Now we branch on carry set. So if after this compare, which basically does a subtraction, it influences the carry bit. So we test on that, and if whatever is in the accumulator is greater or equal to the thing that we're comparing to, then this branch is done. So basically it says that the accumulator holds the Y position for the enemy. And if the enemy's Y position is greater or equal than that of the player, then there's no touching. We've subtracted the value, and if one, we've subtracted the object height. The result of that is compared to the actual position of the enemy. If one is larger than the other, then there was no touching. To be honest, there is a tiny mistake that we're accepting here, because branch on carry set checks for greater or equal. So that means that there's also a no touching when the two are equal, actually. But in Georg's comments, he says, we're accepting that as just a 1-bit aberration, basically. Anyway, not touching in that case. In the other case, they not touching. Let's see. Do we do that now? Not touching basically just returns 0. So that's definitely not touching. It may still be touching. We're not sure. We've done one, but we have to check another case. Namely, we've just subtracted one object height. I'm going to drag in this case again, because we have to check the case that, I'm going to draw a new one. If the enemy is above the player. Now, we've just subtracted one object height. We have to add that back to get to the original position, and then imagine we're here. We have to add another. So that's why we're adding 2 objects heights, because we've just subtracted one. We have to add one. We have to add another, and then subtract one to get to the right level. So basically, we do the same. We compare that to the player position. And the same goes, except we do branch carry clear, which is the other case, not greater or equal, but it's smaller than, which is what we need to test this case. Again, the same explanation. Drag it back quickly. If it's in this case, if the sprites are in this position relative to each other, and we add one object height, 1, 2, in that case, we would end up here, which is great because that would be touching. Possibly, in the sense of the Y direction. We haven't tested the X direction, but we're actually we can say that we're not touching. There's a chance that we're touching. Now, okay, we've done that. In this case, the relative Y positions say that we may be touching. Now we have to test for the X position. Is the X position the same? This is where that happens. The X again is the index into the sprite table. And here's the problem. When we do this, we have to realize that the player's X position, again, is 9 bits long. Remember that we had that 255 border that doesn't cover the entire screen. So we have basically an extra bit in the X position. Now, doing the same calculations, the subtracting and the adding for 8 bits is easy because that's just, the 6502 and the 6510 can just do that. But for 9 bits, we have to do all kinds of extra things. And to get around that, to basically not have to do that, we have to think of a little trick. And what we do is we divide the exposition by 2. That's what we do. And it took me a while before I really understood why and how that works. Well, we do it because of the 9-bit thing, because it would be too difficult to, or perhaps take too long to actually do 16-bit math on an 8-bit computer once every loop. There's no wonder that this happens after the Y checking, because this may take too long. Anyway, when you divide everything by 2, basically you get numbers that do fit into 8 bits, and there's really no problem. But you have to realize that not only do you divide the expositions by 2, you also divide all the distances by 2. So now we're not looking at an 8-bit sprite, a sprite that is 8 bits wide, but only 4 bits wide. I would have missed that. And if I had even thought of doing it this way, I would have missed that. I think this is a bold way of solving a problem. It does feel like a bit of a shortcut, but it does work, and why not use something that works? So here's how it works. This says we calculate a simple exposition, which is just the x divided by 2. We store that in parameter 1. We set the index to 0, and we get the x divided by 2 for the player. Now, basically, we do the same thing. We set the carry, we subtract 4, which is 1 sprite width, divided by 2, mind you. And we check to the right. We compare to parameter 1, which was the enemy player. If they don't match, then we're not touching. Otherwise, we check the other case. And if this case, we have to add 8, which is 1 times 4 for the previous subtraction, and then 1 times 4 for the next one. We don't subtract 1 here for some reason. I did look at that, but I can't really recall how or why. There's even a little bit of German here, Anfang, which is start in German. So we add 8. We do the same compare. If it clears, then we're not touching, and otherwise, and in this case, we're definitely we've done all the checks. The check below, the check above, the check to the right, and the check to the left, and we're definitely touching in this case. So all we have to do now is return 1 to the calling routine. So we load the accumulator with 1, and we return. And the rest we've already seen. Let's look at how we calculate the simple exposition. Basically, we check whether or not the bit is in the sprite is in the extended section of the screen. So we load the corresponding bit. We AND it with the extend byte, so we get our bit, and we can test that. If it's 0, then there was no X bit, so it wasn't in the extended section of the screen. If it was, we get the exposition, we left shift it. No, sorry, we logic shift it right, not left, right, which means divide by 2. We clear the carry and add 128, so we set the 7, bit number 7. So what we do is we divide by 2 and add 128. I don't know, and I can't see that is actually necessary. Couldn't we just leave that out? Or would that confuse matters? I don't know. No, because if one... No, it doesn't. If we're comparing sprites that are in two different sections of the screen, we have to make a difference between that. So that's why we set the 128. And obviously, nothing that divides by 2 is going to be so far to the right that it's across the border. So this would work. If the X bit was not set, then we just divide by 2 and we're done. It's basically that simple. So the accumulator holds the X position divided by 2. And if it was in the extended section, what we're basically doing here is using the 9th bit, and we're using it in our 8-bit section that we've just created by dividing everything by 2. I mean, this is smart thinking. This is how are we going to solve this problem of having to compare 2 X positions that may be larger than 255. Damn, that's and if you divide everything by 2, sure, you have to think of the fact that not only do the positions divide by 2, but also the distances between them. So if one sprite was here and one was here, and we divide everything by 2, then also the distance between them is halved. So we have to crunch everything together. That doesn't mean that these sprites are actually getting smaller on screen. It's all a model. So somewhat theoretical, but it works. We've seen it work. Right. Well, I think that's long enough. I am going to have a look at why that object goes through characters but not down. So maybe that block checking is only done when it's going down and not up. I don't know. I'll have a look at that, but I'll do that offline. Thanks for watching. We're at 10% now because we've done the 10th episode. Thanks for sticking with me. Again, if you have any questions, don't hesitate to ask. And if you have any suggestions, please do so. And I'll see you in the next episode. Bye-bye.